So now, with our background theory out of the way, we're ready to talk about the main concept of probability. So probability is the study of how likely something is to occur. So in very simple terms, it's the study of chance. So to understand that a little bit better, we can define the term of an experiment, which we did in our first episode, but we'll do it again as review. So an experiment is a process where the outcome is uncertain. So as an example, let's say we're tossing a coin 3 times. And we'll say it's a fair coin, so it has an equal chance of landing heads and an equal chance of landing tails. So if we draw our tree diagram, on our first toss, we can land heads or tails. On the second toss, once again, heads or tails. And the same thing for the third toss. So now, we know that this first branch and every single branch is a possible outcome. So this first branch corresponds to the outcome of getting 3 heads. Each one of these outcomes is called a simple event. So each outcome corresponds to something we call a simple event. And in this case, we have 8 simple events. So heads, 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 tails, all the way through all of these 8 simple events. If we group up these simple events, grouping these simple events gives us the broader term of simply an event. So if we group multiple simple events together, we get an event. So an example of an event would be all outcomes where we land heads first. So the event heads first is going to be equal to everything in this first block. So heads, 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 tails, heads, tails, heads, and heads, tails, tails. So the event of landing heads first is equal to this. And the collection of all simple events, or in other words, all possible outcomes, that's called your sample space. So usually the sample space takes the letter S, and in this case it's equal to all the outcomes. So everything in our tree diagram. So that would be heads, 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 tails, heads, tails, heads, heads, tails, tails, and then we can keep going. So our sample space is composed of all the 8 possible events. So in order to calculate the probability of an event, so say we have the probability of some event, it's equal to the number of successes, so outcomes that satisfy the event, divided by the number of total outcomes, or the total number of outcomes. So for example, if we're flipping a coin once, and it's a fair coin, then the probability of landing heads, our success is simply landing heads, so we only have one success. Our total outcomes is either heads or tails, so we have two total outcomes. So the probability of landing heads is 1 divided by 2, which is equal to 0.5, and if we multiply that by 100%, we get a 50% chance of landing heads. And if we go back to our previous example with our tree diagram and flipping a coin 3 times, so flip coin 3 times, the probability of landing heads 3 times in a row, there was only one occurrence, which was at the top of the tree, and that's getting all 3 heads, divided by our total outcomes is the same thing as saying our sample space, which had 8 total events. And so the probability of landing 3 heads is 1 divided by 8. And usually, in any class, you can leave your answer as a fraction, a decimal, or as a percentage. They're all accepted. Now, when talking about probability, we have a few rules. So since it's a ratio between some number of outcomes that are preferable, or called successes, divided by the total number of outcomes, then the probability of any event has to be greater than 0 or equal to 0. So your event could be impossible, could never occur. So for example, what's the probability of landing a 1 when I'm flipping a coin? It's not possible to land a 1. Your only outcome is either heads or tails. So the probability of getting a 1 when flipping a coin is 0. So the probability of any event has to be greater than or equal to 0, can't be negative, but it also has to be less than or equal to 1. If your probability is equal to 1, that means you have a 100% chance of getting this event. So another example would be the probability of getting heads or tails. The probability of getting heads or tails when flipping a coin, those are your only 2 options, so it's guaranteed. So that means you have a 100% chance, or a probability of 1, but it can never be greater because that wouldn't make sense. The second rule is that the probability of getting an outcome that is in the sample space has to be equal to 1. What this is saying is that the probability of an event inside all possible outcomes is guaranteed. Which makes sense, because S simply means all your possible outcomes. The probability that your outcome is within all the possible outcomes is guaranteed. So now for an example, we have a bag that holds 3 cards. One that's red, one that's blue, and one that's green. Our experiment is we pull a card out, place it back within the bag, and then select another. So in this case, we want to know what the sample space is for our experiment. So for A, what the sample space is. So if we draw a tree diagram, we can either pull out a red first, a blue first, or a green first for our card. After that, we have 3 outcomes. So red, green, blue, red, green, blue, red, green, blue, and that's our second choice. So our sample space in this case consists of 9 possible outcomes, and that's red, 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 green, red, blue, or blue, red, blue, green, blue, blue, or green, red, green, green, and green, blue. So we have 9 outcomes. And we can check our answer with our counting rules, since we know we have 3 options for the first selection, and we have 3 options for the second selection. That's 3 times 3 total selections, or total outcomes, which is 9 total outcomes. Now for part B, we're asked to find the probability that the green card is never selected. So the probability that we do not have green. So P of not green. So the number of events that don't have green consists of red, red, and red, blue, because we can't have red, green, or blue, red, and blue, blue, because we cannot have blue, green. And anything where green is selected first also is not in our successes. Divided by our sample space, which has 9 total events, then the probability that we do not have green is equal to 4 over 9. And another way you can check your answer, so the probability of not having green, since these events are independent, which means that if I pull red the first time, I still have an equal chance of pulling red the second time. The probability of pulling a card doesn't change based on what you pulled prior. And we'll go over that in the next video and in greater detail. But for now, just an interesting way you can check your answer. The probability of not pulling green the first time, so you can pull either blue or red, but not green, is 2 out of 3. Because we can pull blue or red, divided by total would be blue, red, or green. So the first time of not pulling green would be 2 out of 3. The same is true for the second time. So multiplying these two together, we also get 4 out of 9. Which is generally true for any two events that occur in succession where the outcome is independent, or the probabilities are independent. So just as a final clarification before we end the video, when we calculate the probability, we're calculating a theoretical probability. But of course, we can also actually perform our experiment and find an experimental probability. So in that case, our experimental probability would be the number of times our desired event occurs, number of times event occurs, divided by the total number of trials for our experiment, or how many times we repeat our experiment. And this gets closer to the theoretical probability as the number of trials, or n, gets bigger. So in the case of flipping a coin, suppose you repeat the experiment only one time. So we only flip the coin once, and that's it. Then the probability of landing heads, perhaps we land heads the first time, so that's going to be 1 out of 1, or 100%. Or maybe we land tails the first time, so it's going to be 0 out of 1, or 0%. And so at the moment, our experimental probability and our theoretical probability are pretty far because n is a small number, it's equal to 1. But if we increase our number of trials, so maybe I flip the coin 1,000 times, then in that case, maybe you'll land heads 510 times. Or maybe you'll land heads 480 times. In that case, your probabilities are going to be 0.51 or 0.48, which are both very close, or approximately equal to 0.5 or 1/2. So your experimental probability gets closer to the theoretical probability as n continuously gets bigger.